here, I will make it as twice pi. So what is this time now? This time firing angle comes in terms of my theta. Okay, so that means your twice pi by t into this t becomes my alpha in radians. Okay, twice pi by t, capital T is the time period here, into t becomes your angle radian. So your firing angle is your alpha, that can be controlled by some circuit to serve the your VI characteristic, current voltage and current characteristics of the negative resistance devices. So that way this firing angle is controlled. This you have, I think, seen in some kind of your, in some sense to the your coverage of module number 3, not 4. In 3 we have done that. No, in module 4 itself we have done that. Okay, so that is the one. Now we also seen in module number 3 how to generate a voltage. This is my voltage. This is my 0. This is my V. This is my T. A stable multivibrator. Voltage is coming. You can see that. We have also seen that this is my A stable. A stable circuit from the capacitor, resistance, charging, discharging. We have seen there a stable multivibrator giving the square wave output. Now we have also seen that output should come only when this is applied. Okay, your output becomes your 1. This is my V input I'm putting. When this is applied, my output will be, a switch will be your on. Switch on I'm saying. Okay, output will become 1 because switch will become on, switching circuit will become off at that time anyway. So here I'm putting your V out of switch. It remains on till the next pulse is appearing and it becomes off at that time. When the third pulse appears here, it becomes on again and so on. So that's what it will remain till the another trigger is applied like that. So this one will be your T, this is your V. So this is your, I call it monostable. Sorry, bistable. And the monostable I described was when this is given, this will become on and it will start decreasing. It will come to this 0 voltage here. This is not needed. It automatically come at this point. It will remain 0 till another pulse comes. Here again it starts falling. It will come to this 0. This will not needed. So this is on a stable circuit. It comes to the stable state automatically. So this one will be monostable. Okay, these are the circuits you have seen. They are very useful in your digital electronics. Now something more we need. It was very much used in your display devices, display systems. Nowadays everything has become digital. So those things are not having much significance, but still on the big screen those displays are there where this direct measurement we want to see. There we want something, let us say V, to get applied to a switch in this form. It is increasing, then it becomes your 0. That's what I want, but it is coming something like that. Okay, it is coming something like that. Then from this point, it starts increasing. It is same thing, same circuit. Not coming to 0, coming something like that. And it starts from this. So this we call as sweep time. The voltage is sweep time, sorry. Sweep time from here to here is sweep time. I can say as Ts. What is this? If I leave as it is, it will start discharging the system and it will come to this state. Before the next sweep is applied, it comes to the 0 and remains 0 there. Okay, so from here to here, we call it a retrace time. So this kind of circuit we need to make. Why? Because if I apply this on to a display system on the x-axis, it is increasing with respect to time. So with respect to time, it is going like this. Voltage is increasing. So this is low voltage, high voltage, higher, higher. This is your, I'm calling as my Vs, but this is my Vs. So 0 to Vs, it is increasing on the x-axis deflection plate, and that is calibrated with respect to time. The slope into this time becomes your this tracing. Conversion of time to voltage will be your slope into time becomes your voltage. So slope into time is voltage. It is growing like that. So it is calibrated to time now. Now on the y-axis, some signal is displayed with respect to time. This is my y-axis. This is my ST. It displayed something like that. It can be of any form. It is displayed, and this will be periodically coming. This portion will be periodically repeating. So what happens at time t equal to this 0, it is this voltage. So here that voltage will be appearing here. T equal to 0, that voltage is appearing. Then if I am increasing by t here, at the same time the x-axis voltage is also changing, so it will be shifting to some other location in the x direction. So here it will be coming like this, and that's how it will be going like this. Here it will be coming something like this. Here it will be coming something like this. Remember, it is not hanging in the air. It has to touch some datum there. So if it is your 0, before that, if it is this point, it is here to here. At this point, it is becoming your 0. It is starting from the 0, so it will be starting from the 0. It will go like that. Here it becomes 0. It cannot hang in the air. It has to touch the datum somewhere. That will be as per the definition of the signal and the display system. So sweep is helping us in displaying these things. Now retrace time means when this is repeating, this repetition should start from here. Not from here exactly. And this is your taken as TR, retrace time. This is taken as my TR. Okay, so if this TR delay is there, after that next sweep is starting. So it will be displayed again here. The same pattern will display here again. So any signal can be displayed on the screen by putting X and Y two deflection plates for the electrons, and it works. So that was used in your cathode ray oscilloscope, even your television system, and even in your radar system. Everywhere it was finding the use. Now in digital case, this technology is changed, it is brought in some other form. So I'm not talking of digital TV, I'm not talking of the digital radar display. Okay, that will be a different domain. So today in this class we'll be talking about this analog. We want to reduce this retrace time. So what we do? We'll make a circuit like that. Here the switch has become on. And the switch has become on. You see on, then this sweep will be generated, and when the sweep is generated exactly at t equal to Ts, the switch is off here, switch is off here. Here is my input, something input V minus plus, something like that is coming with my V. Okay, and here is my device to which I am applying. When the switch is open, okay, it is creating a sweep at this output. Here is my sweep. Okay, when the switch is open at this point, this device is giving me a sweep. Now I want this to be retest time to be 0. So when at that time t equal to Ts, switch is closed, so it becomes a short circuit. So what I am getting here to Ts, it becomes 0, and next cycle starts from here itself. There is no retrace time. So even if signal is coming continuous, during this period I am not losing any display. So that's what will be coming like this, coming like this. And like that. So this is your voltage V, and this is your time T. So we want to generate a sweep of this kind. Second thing, my display should be exact reproduction of my input signal, whatever I want to see on the screen. Okay, so what happens? This T time to voltage conversion, okay, it should be linear. This conversion should be linear. If it is linear, exactly linear, it is having no compression or no expansion in the signal. The exact display will be there. When it is not linear, either it will be expanded or it will be compressed in some portion. That's what we want to avoid. So purpose is that sweep should be linear and it should become exactly 0 at t equal to Ts. That means switch should become off immediately. So switch design is so that it becomes 0 voltage across it moment it is switched on. So these are the purposes we are going to address in this module number 5. You already know the things, so we will not be having difficulty in progressing at a comfortable speed, and you will be able to interact and understand it suitably. Okay, so I come to the analysis of that. How do I get it? Capacitor you have seen. Suppose I am charging with respect to a voltage V, and through this resistance R, I am charging a capacitor here. See. Okay, and here I'm taking my BC. V naught equal to BC. Okay, and at certain time sweep duration, I want this switch Ts, or you can say at T equal to delta, sorry, T minus NTS the switch closes. So after every Ts seconds, Ts time, output will become 0. Okay, so what do you get? Vc, if you remember, it was your V into 1 minus e to the power minus T by RC. Am I correct or any mistake? Just to correct me. V naught is Vc, that is V, this voltage, 1 minus e to the power minus T by RC. It is going like that. If I expand it, what I am going to get? Equal to V 1 minus 1 plus T by RC minus T square by factorial 2 into RC plus here minus that's why I'm going to get it to the minus T by RC. Okay, so whenever minus was coming in the expansion of e to the minus T by RC, that becomes plus because there is a minus sign here. Minus I've taken outside. So that will be your T cube by factorial 3. Okay, T square by RC square, sorry. T square by RC square, T cube by RC cube, minus something and so on is the expansion. So what do you get? This 1 and 1 gets cancelled. So I'm getting here as V into T by RC minus T square by factorial 2 RC square, X square by factorial 2 that way, plus T cube by factorial 3 RC cube and so on. Okay, so this is my V naught. At T equal to Ts I am interested. When Ts is large, okay, all these terms will be appearing. T equal to Ts, all terms will be appearing. Okay, now when Ts is small, when Ts is small, that means T which is less than equal to Ts, there I am interested. So what happens? This higher order terms will vanish. Okay, so if Ts is small, it will be V into T by RC. Okay, so we will be getting here V naught equal to approximately equal to V into T by RC is Ts rather. Okay, V into T by RC for T going from 0 to Ts. Okay, T going from 0 to Ts, it will be V into T by Rc. Other things are not coming. As a result, magnitude of V naught is much smaller than magnitude of the V. Okay, so in this process, what I am losing? I am making Ts as very small, then magnitude of V naught, maximum magnitude of V naught will be V that I applied in very small Ts by Rc. Ts is very small. Okay, to satisfy this, so at that time, my V naught maximum is very small. V naught maximum, that is nothing but my Vs is small. Okay, so Vs magnitude of the sweep is very small, only then we are applying this, but we can apply that. Okay, so this constraint, one method is to keep your sweep amplitude as small as possible. That is the first method of getting that. We have seen that it is going something like that. It is going like that. This is the way. Okay. This is my V naught. This is my T. So here is my Ts. If Ts is very small, and this will be my Vs. Amplitude of the sweep. Slope will be there, of course, controlled by your RC like that. So this is the one we have got. First method we have got to realize the sweep magnitude very small. If that is small, that means T is very small. It will be a linear kind of variation. I can get it. Could I explain it? I read it out. So sweep can be generated to very small peak with a linear characteristic. And here at that particular Ts, this switch S will become on. So it will become 0 at that point Ts. So at Ts it will become 0. Again it will start going like that. Become 0 again, something like that. It will be coming because of this switch. Switch closes at Ts, 2 Ts, 3 Ts like that. So it is the way we are controlling this kind of a linearity characteristic of the sweep voltage. Is it okay? My purpose is to increase the magnitude of the sweep, peak of the sweep, Vs I want to increase while maintaining the linearity. Okay. So there are some methods I can say, but first one I put it here. First I explain keeping very small. This means Vs is small. This is the first method. Second method is using for charging. The capacitor. So how do you get it? There are various versions in that. How do you get it? This one. Here I'll make a constant current source. Okay, constant current source. Here is my applied voltage. V. Source will give me constant current. That current will be my I. So some combination in the circuit will be there. That will be constant current source. This is my V. Here is my capacitor. Here that R is on because your exponential increase, etc. through your time constant. Here the concept of time constant is not coming. So what is my this V naught? Vc is equal to V naught will be equal to V naught is what? 1 by C integral I dt. Okay. And this I is constant now. Constant current. So that is your constant current I by C into T. Okay. So our V naught is I divided by C into T. So how much is the constant current for this applied voltage V is coming from the circuit that will control the sweep voltage. So here the sweep voltage will be Vs will be current I by C into Ts. So Vs will be 1 by C, sorry, I by C into Ts, that is the sweep amplitude. I can change the value of the constant current for any Ts. My Vs can be increased. Even if Ts is small, my Vs can be higher. If Ts is increasing, Vs is increasing, that is understood. But I am keeping my Ts under constraint of my design, but I am increasing my I. So my Vs, peak is going up. So I can make a sweep like this for this Ts. I can make a sweep like this. I can make a sweep like this, depending on the change in this constant current source. Voltage V and this constant current are accordingly designed. So even for same V also I can increase the current in that source design, that can be seen. Or if I increase my V, even then for that also I can change my I like that. That is the constant current source. So it is, if I am able to make like that, it is giving me a linear sweep. See, remember this I is having a unit of a current, but it has got the magnitude. Here I am getting the magnitude. This by C becomes your 1 by T, sorry, voltage by T into T. So becomes your voltage. Output becomes your voltage. So that way I will be able to get some desired sweep peak for a given required Ts. Okay. Is it okay now? Constant current source, plenty of circuits are there. I'll come to that in some discussion is there. Fundamentally, I am using this. Okay. Third, realizing constant current charging by feedback. Okay. Purpose is constant current. Okay. So there will be a capacitor. Through capacitor, constant current will be going. That concept of time constant will not come here also. So it is the same thing. So what we are doing here is, suppose this is my voltage V, this is my R. For the time being, I am considering my R. Okay. And this is my C. This is my C. This is my output. We have seen it is not linear. Okay, it is not linear. The circuit is modified. This is my voltage source V. This is my current R. This is my capacitor C. I want to get voltage across this C. Okay. Instead of getting the voltage across the C, what I'm doing, I am putting a source here by feedback. This voltage has come from the feedback arrangement. In the way, if the capacitor was charged, this was your plus, this was your minus, this was my VC. This voltage I want, this becomes my plus, this becomes my minus, and magnitude becomes your VC. I make a feedback, I add it here, this voltage source. Okay? So this voltage source, when added here, has given me option how to work in different conditions. This is my R, this is my C. This has come as a voltage source from feedback. Voltage source equal to minus VC coming from feedback. Okay. Now let us see. This is my X. This point I'm calling as my Y. Sorry. This point is my X. Okay. This is my X. This point I'm calling as my Y. This point I'm calling as my Z. Okay. Suppose I'm considering the input at X. and measuring the output at Y. Input is given to X and Z. My VXZ, VI is VXZ. This is my amplifier. Something is coming. In which system I am giving, this is going to be my input now. This is my input. So VXZ is my input, and I'm taking my V naught as ZY. Okay, V naught I'm taking at VZY. V naught is what? Nothing but minus BC. Okay, VZY from here to here, the same thing in the magnitude, it is minus BC, which is coming between X and Y. X, Y, I am not taking here as a reference. I am giving input here, I am taking the output here, where the feedback also has been connected in this manner. So across the feedback, I am taking the output now. Okay, so what is going to be my V naught now? VZY, VZY is my VC. Okay, how much is current flowing through it now? Let us see. How much is the current flowing in this circuit now? Plus VC minus VC will become 0. This plus this. What is the equation? I will write your loop equation. Loop equation, no equation. That no, I think voltage law, Kirchhoff's voltage law I can apply there. So it's your V. This is my V plus IR minus V plus VC minus VC becomes 0. In this complete loop, suppose I want to write an equation, it becomes like that. So how much is the current flowing through this loop now? I'm giving input here, I'm taking output here. So how much is the current flowing through this loop? VC and VC cancels here. Okay, so here is your I into R, V equal to I into R. So it becomes your V minus IR, V plus IR. V minus IR, sorry. V minus IR, this will be my VC, this will be my plus VC, sorry. V minus IR minus VC plus VC is going like that. In both cases, VC gets cancelled. So what I am getting here is V equal to I into R. So current flowing through this is I is nothing but V by R, and that is V is constant, R is constant, so current is constant. So capacitor is charging with a constant current, but at the output what I am getting? Negative of that. The sweep will be negative. If I am taking output between Z and Y, Z is ground. Remember, Z is ground. V not equal to VYZ rather, not some. It is VYZ, sorry. I can write here VYZ. Z is ground. VY, it will be your minus VC, so like that. So this is the way we have got it, like this. So current charging the capacitor will be this. So capacitor will be charged. This is the voltage across the capacitor. And when the switch, there is a switch here, that switch will be closed at T equal to delta T minus NTS. So it will be closed like that. So it will be getting a sweep like this at voltage across the at capacitor, or you can say across capacitor. Capacitor C. This is my V, this is my I. At the output, what is my V naught? V naught will be having a negative flow, like that. So this is my V naught. This will be my T. So slope will be negative, but it will be having a linear slope, and that will be controlled. That slope will be controlled by this I, and I is nothing but ratio of V by R. By adjusting V and R, I can adjust my I, and that I can give me a linear sweep by this adjustment. So what way this feedback is coming? We'll talk to that in forthcoming lectures. How to get this VC equivalent to this minus V, this will be minus VC equal in magnitude to this VC. So that way it will be your first method. Is that okay? So constant current charging is realized by feedback control. So I just take a break here. I will be taking up other issues in the next class. I welcome any question related to this, or I'm coming back to my discussion on the solution manual for the circuit. Okay, so what is that opinion? Question from the quiz number 4 should take, or what is that? Anybody has got out about question number 4? Answers are mailed to you. So Sen Gupta, is there any feedback to you? They have given any feedback? Which question they want to discuss?
The answer is not uploaded. We have not uploaded the answer, but we have evaluated it. They can see their answer whether it's wrong or correct.
Unless the answer is given, how can they get the doubts? Anyway, I'm going to upload my this thing. I'll show you my file first. Okay, then I will upload in a couple of minutes. I will upload that. I'll show you my file. Okay.
Okay.
Quiz. Can you see this? Is my screen visible to all the students?
Yes, sir. Visible.
Yes, sir.
Yes.
Visible now? I'm just increasing that font size. Okay. I'll upload this as a file in general section. Name will be same thing. EC353 quiz 4 solution. Okay. So you'll see that. I'll just make it. I'll explain to you what way it is on. Okay, you can see question number 1. Considering the positive and negative resistances of the device, which are constant, that means the slope is constant. Okay, resistance is constant, I mean slope is constant. It is linear slope. The negative resistance value can be written as positive, negative, both. Here I have given the question, sorry. I have given the question here. Yeah. Here I have given the question. Having the break points 3 volt 1 milliampere, 1 volt 5 milliampere. One is your valley point, one is your peak point. You can take like that. So 2 points are given to you. So you are having 3 different slopes. slope number 1 and 3 for the positive resistance will be the same, that you can compute from the first slope itself. Third slope can be derived. It will be going from peak point onwards, where the first point going from 0 to valley point. And the negative resistance, that slope is effective in between peak point and valley point. Okay, so that way you know, find the equation of the straight line, you will get the answer. I have given the values like that. Negative resistance 1 minus 3 delta I, sorry, delta V by delta I is your negative resistance. No? So delta V will be 1 minus 3, 1 volt is here, 3 volt is here. So 1 minus 3 negative voltage, and current will be 5 minus 4 positive current. So this negative resistance value will be minus 1 by 2. Okay, so here Rn is something like that. The negative resistance value can be written as 1 by 2, 1 by 2K. So this is what I have given. So you see that I have given the answer. I have given the solution manual also. How, what way it is coming? Unless you see that, how can I discuss the problem in that case? I think your section should put the answers immediately. And after the test, you should tally your questions. Okay, anyway, I'm going to upload it now. So no question today in that case. Okay, am I correct? From your side, you don't have any question. Question 5 is just like your, statement kind of thing. I uttered in the class also. I will explain that what is happening there. Okay now? So in the next class also we'll take questions. You will see that I'm going to upload in a couple of minutes. Before going for any other work, I will upload that file to the general section. Is it okay, President Gupta? Is it okay now?
Yes.
Okay. So good. So good day. I'm uploading that. I'll see you in the next class, which will be on Monday now. But anyway, you come prepared with all things. I have given the solution manual for everything.